In this video, we'll discuss logarithmic models. Now we can define the log of x to the base b equals a as an exponential equation as well, where b raised to the a equals x. These two statements are equivalent to one another. So if I have one, I can convert it to the other. So say that I have 6 to the third equals 216. We know that's a true statement. We could convert that to a logarithmic equation. We just have to recognize each of the parts. In this case, the base is 6, the exponent a is 3, and the x value would be 216. So we'd substitute that into the equation and say that the log of 216 to the base 6 equals 3. One of the nice things to remember is that both the log and the exponent have the same base. So that's a way to help you remember where parts go. So the log of 216 to the base 6 equals 3. What if we wanted to go the other direction? We start with the logarithmic equation, and now we want to convert it to the exponential equation. So we have to recognize again, our base is 2, our a value from the logarithm is 7, and then our x value is 128. We substitute those parts into the exponential equation, and we have 2 to the 7th equals 128. Now there are several specific logs that can be very helpful. The common logarithm is a logarithm with a base of 10. So if you ever see the word log and then a number in parentheses, that's the common logarithm. If it's not written with a specific base, it's implied to be a base 10. On your calculator, you will see a log button key that you can push. And so when we do them, if you need to simplify, we can always hit the log and then enter the number, and it'll give us a solution. So say we want to convert log of 10,000 equals 4 to the exponential equation. The key here is remembering there's no base, so it's implied that it is going to be b. So we know the log of x to the b is equal to a. So we have to think about our base in this case is 10. We have our a value of 4 and our x value then of 10,000. This means that 10 to the 4th equals 10,000. Another specific logarithm that's important to recognize is the natural logarithm. This is a logarithm with a base of e. Now, we don't write it as the log of x to the base e. Instead, it's written with the letters ln of x, which means natural log of x. So we know that the natural log of x equals a will be equivalent to e raised to the 8th power equals x. On your calculator, you'll look for that ln. Sometimes you may have to hit the shift button or second button to pull up the natural log, and often it'll have either an e or the e will be the shift part because they're the inverse functions of one another. So say we want to convert e to the 5th equals 148 and 413 thousandths to its logarithmic equation. We know then, again, we're starting with the exponential, and we're going to convert it to the logarithm. So we know that the natural log of x equals a, where our x value is 148 and 413 thousandths, the a value is 5. So the natural log of 148 and 413 thousandths equals 5. Now say I want to evaluate on my calculator. I'm going to use the log key or the natural log key, and then I'm going to close the parentheses after whatever number I'm entering. And we just have to remember that if we use the log key, that is a log that has a base of 10 for that value. So when I do log of 100, the calculator should shoot out 2. If I take the log of 426, that's going to shoot out 2 and 629 thousandths, and I'm rounding to the thousandth. It goes on much longer than that. If I did the natural log of 32, that would simplify to 3 and 466 thousandths. Again, that's rounded. Now, what if I want to simplify the natural log of negative 6? If I enter this in my calculator, it will come out as undefined. So the question you might be asking is, why? Well, think about its equivalent exponential statement. We have e raised to the 8th power equals negative 6. Well, there is no value of a that I can plug in that will make this become negative 6. So it's not possible. That's why we can say it's undefined. Now with inverse functions, we know the logarithm of base b is the inverse operation of the exponent of base b. So if I place a logarithm in the exponent or the exponent in the logarithm, they'll simplify and leave me with the value that is representing the x in that situation. For example, 4 raised to the log of 32 to the base 4, the log of base 4 and the 4 will simplify and leave me with 32. If I have 10 raised to the log of 86, this is a log with a base 10. The exponent and the log will simplify, leaving me just with 86. If I had the log of 5 to the 9th with base 5, the base in this exponent base will leave me with just the 9. If I had simplifying the natural log of e, well, the base of the natural log is e. This simplifies to 1 because they're inverse. It's like saying 12 divided by 12, and that equals 1. Now, if I want to graph, I'm going to remember to use my parentheses and use the calculator to help me approximate values so I can get some points, and I can use that to help me form the curve. So if I had 3, the natural log of x plus 2, I'd want to say, okay, let me start using some values. So maybe I'm going to go 0, a tenth, 1, 2, 3, 4, 5. So I'm going to take each of these values and substitute them in for x and see what my ordered pair becomes. So if I substitute in 0 for x and I simplify, that's undefined because I can't do the natural log of 0. If I plug in a tenth, I would get 3 times the natural log of 1/10 plus 2, and I simplify, and this would come to negative 4 and 908 thousandths. So I do have an ordered pair. So if I think about it, I'm going from undefined to this ordered pair, there must be some very quick asymptote there at 0. If I substitute in 1 and I start simplifying my expression, I would end up with it equaling 2. So I'd have the ordered pair 1, 2. If I substitute in 2, I simplify, I'm going to end up at 4 and 79 thousandths. So I have the ordered pair 2 and 4 and 79 thousandths. I can do the same thing with 3. I'm just going to substitute in, close my parentheses, add 2, and get 5 and 296 thousandths. We have my ordered pair. I can do this for 4. That'll simplify to 6 and 159 thousandths. And at 5, I would end up with 6 and 828 thousandths. Now look what's happened. I've gone from being undefined, that very sharp asymptote, to it's changing quickly, but as you look at those numbers, they're starting to curve and slow more and more. They're getting closer and closer. That y value is not changing as much. And that's what happens when you actually go to graph this. If I plot those points, you can see it's starting to curve less and less. And if I overlay the actual equation, it would look something like this. Now we can also use logarithms in actual real-world problems. For example, the relationship between the number of decibels of sound and the intensity created by the sound can be found by the following logarithmic function, where d is equal to 10 times the log of the sound plus 120. So normal conversation has an intensity of about 10 to the negative 6 watts per square meter. About how many decibels would normal conversation be? So we have to think about, what do we know? So we have a formula that's provided, and they're telling us that the intensity, that I value, is 10 to the negative 6. So I can now simplify this expression, and I can say this is log base 10 of 10 to the negative 6, which would leave me with negative 6 here. Or I could also plug it in my calculator, and it was simplified for me. So I have negative 60 plus 120 tells me that the decibels of normal conversation is about 60 decibels. Now, what if I wanted to use a little bit more complicated formula here, looking at population growth? So I know that to determine population to reach a certain size, I can revise the formula from P equals the initial population raised to the e to the kt, and I want to find out instead how long it will take. I could rewrite that as t equals the natural log of p divided by the original population divided by k. So if the US population was 320 million people in 2020, with a growth rate, that's our k value, of 59/100%, in what year will it be 400 million people and round to the nearest year? So we have this new formula where we're solving for the time. We're told that P is that new population that we want to know, which is the 400 million. The P naught was the original population, which was the 320 million people. And we're told this growth rate as a decimal. So 59/100% we would write as 59/10,000s. We want to divide that by 100 so that we're actually dealing with the decimal and not the percent. So I substitute in my values. And again, this is the time since 2020, so I'll have to remember to add that on. So I'm going to substitute in what I have. So 4 million divided by 320 million, I'm going to take that natural log and then divide that by the 59/10,000s. So I can simplify and say I'm really looking at 400 divided by 320, which is a little bit easier to write in my calculator and simplify. And that'll give me about 223,144 millions over 59/10,000s. Again, I divide that out, and that'll give me about 37 8/10, or about 38 years. And I got to remember, that's 38 years since my start, which was 2020. So 38 plus 2020 would say that in about 2058, the population of the United States will be around 400 million people.